we've sort of covered part of it, but we haven't covered the other part of it. And you guys will notice that my folder is like empty. I filed away all kinds of notes. I did scan in the 2 problems that we did last week. I just haven't uploaded them onto Blackboard yet. So early on, I seem to recall that I drew things that look like this. And partially it's because that is recording. Life is good. It's because I was trying to explain positives and negatives. And so this is our high temperature reservoir. This is the low temperature reservoir. And we're going to have heat flow. And we're going to have heat flow. And we're going to have work going out. So this is referred to as a heat engine. Okay, and this is also a way, we're getting ready to do the second law of thermodynamics, and the second law of thermodynamics says I always am going to lose heat, and this is a rate of heat transfer. I'm always going to lose heat to a low temperature reservoir. I can't have it go 100% to work. And this is they usually will designate this with an H, they'll usually designate this with a C, but you're watching the heat flow, and this is our heat engine. And what we will end up doing is we will define something as the thermal efficiency. And this is the very last part of chapter 4. And our thermal efficiency, we're going to use this lovely little scripty n, and that's the work divided by our heat. And of course, we can do the same thing if we can do it on a rate basis. We can do it on a rate basis as well. And these are going to get us to our various cycles. We're going to start talking about different cycles that are out there. There'll be the Otto cycle, O-T-T-O, and that is like my diesel engine cycle, my gas compression engine cycle, all of those things. And to be fair, the efficiency, the thermal efficiency of an internal combustion engine isn't all that hot. It's great, you know, I think the ideal Otto cycle is like 49%, which would be the absolute maximum that you can possibly get. But we can do an awful lot of things with our cycles. Okay, we can do an awful lot of things with our cycles. So we could actually, you can also do this, you can call this a heat sink. So that gives us our terminology that we do. We get to the heat sink. And so you can look at it and calculate. So one of the problems, one of the examples they give us, they get work while producing heat from a source, determine the efficiency. So we're going to start out with the net work generated in the cycle. We're going to get, the work is going to give us 81 kilojoules. And the heat input occurs, so we're going to put in heat input of 257 kilojoules. So calculating the efficiency is pretty straightforward. 81 divided by 257. And that's going to give us 0.315. I'm going to do that. I'm going to double check the calculations. Yep. So we do get, you know, efficiencies, but we do lose a lot to the environment. And just as a refresher, if we are dealing with heat pumps or refrigeration systems. This is our low temperature reservoir. This is our high temperature reservoir. We have to put work into the system in order to go this direction. But now you can start thinking about, well, why doesn't my air conditioner work very well on a hot day? If this is my reservoir and I'm trying to pump more heat into my reservoir is just not going to take it. So we do have challenges as associated with what the temperatures of these reservoirs are in order to have them work. Now for refrigeration, what they do for a refrigerator, they call it a coefficient of performance. And that is going to be, this is going to be the cool part, because that's really what we're doing. This is the cool part, this is the hot part, and I'm dividing it by my work. So we kind of do it reverse and upside down. You can also do a heat pump, but in my heat pump situation, I want the hot divided by the work. And hang on, I'll get that moved up because I know it's not showing. And they always want these to maintain positives. I want those to maintain positives. So those aren't terribly difficult. And I think, guys, that finishes our chapter. That finishes our chapter. And I wanted to make sure we covered that. But I do have one more problem that we can do with a rigid container. But that's all the theory that we need to cover. So we're going to do another closed system problem. We did one on Friday. We'll do this one. This is a closed system rigid container. And we're going to start with a volume of our container is 0.30 meters cubed. And we're going to have 240 degrees C water at 300 kilopascals. The container is then cooled until the temperature of the water is 100. So we're going to start out with our closed container. Draw on our stuff. We're going to put work into the system because we're cooling it. And the work we're putting in is 35 kilojoules. We're going to cool the water to 110 degrees C. And we want to find the final pressure and we want to find our heat transfer. And this work we're going to make negative because it's going into the system. So our givens is our volume. And since it's a rigid container, this is going to imply that it's constant. So we're not going to have a change in volume. Our T1 is 240 degrees C. Our T2 is 110 degrees C. Our P1 is 300 kilopascals. And our work is a negative 35 kilojoules. And we want heat. So we want heat instead of heat transfer, so we're going to work with that. We're dealing with water. We can make the following assumptions. Is that we don't have anything that's telling us about our change in kinetic energy or our change in potential energy, so that's got to equal 0. We've got a closed system. So, and what this, it says both mass and volume are constant. So our volume is constant, our closed system says mass is constant. So I've got to go in and find our changes for our pressure. Do this one. It's going to go into my app here. Okay, so my pressure, I'm going to look at this real quick. Okay, pressure temperature. So my pressure is 0.3 kilopascals. My temperature is 273 plus that. Can't add today. 513. It's 383. Oh, that does work. Okay. So I'm using this app, and I put in the 0.3. Which, because it's in megapascals, I put in the temperature. This gives me my volume. My volume that comes out is 0.780. Now we're making the assumption that volume is constant. So now I can do so this is volume 1, we end up with volume 2. And I want so now if we go back and do the other, we're still at, because we're trying to find pressure. want the volume of the fluid, and we want the volume of the gas. Check. This is our V2, so if I have my X, this is V2 minus V fluid divided by V gas minus V fluid. So we want to do at the final temperature, which is 110. I go here, I'm getting the 0.1052 for my V final, and my V gas is my 0.121. So I'm getting that piece. And that tells me my final saturated mixture is that right there, so it's going to be 143.3 kilopascals. So I'm getting all of this right off of my table at 110. I'm just trying to figure out how to do that on the app. So if I go back, I want to do there, no, I want temperature, so now I can go back to the temperature. The temperature in Kelvin was 311 or 383. So that gave us our pressure. There's our VG. So we can get that part. And then we can also do it by doing this. If I go to 0, 383. There's my BF, my pressure. And then we can set it to 100. Do the calculus, 383. Okay, and that will allow us to calculate this, and if we calculate that, this is going to be 0.645, which does show us that we're a saturated mixture. And then we can do the last part. Try and keep my stuff straight. This time we have to do Q minus W is equal to mass U2 minus U1 delta KE plus delta KPE. Those go to 0. I need U2 and I need U1. There's my U, 2713.206. If I do my new temperature, it's at 0.143, and that was 383. And there's my new U. That's not right. It's a saturated mix. Well, we have to go back here. Okay, except now that's 0.6. 6, 3, 6, 4. That's still, this is giving me a different number. That's giving me mixed. Okay, he did it by doing pressure. So this is going to be 0.143, and that's using our X2, which we have to go back in and do our 65. Now we get to calculate. Now I get, oh, I'm still getting that number. I got that number either way. The U I'm getting is 251. But the pressure I used was the 143 because that's our P2. Double checking. .143. That's kilopascals. MRK. Yep, that's actually giving me the right, and I'm getting a different value. I'm getting, like I said, I'm getting this value right here. The value he worked the problem with is this value. But that's the value I get for the second one. Our mass is going to be our specific volume. Oh, okay. Our volume was 0.3 meters cubed. And our other volume is 0.7803. .385, and that gives us that gives us those two things. So the Q I come up with is going to be our 0.385, our 2517.58 minus 27.13 minus, because that's plus work, but our work is negative, so that's 35 kilojoules. So I get, that's not a rate, that's just Q. I get a negative 110. And he got a negative 391. But I can tell you where my difference is I'm getting that number, but let's look at this steam table and see what we would have gotten. So if I'm at 110C, yeah, I still, because if we're doing exactly the same thing, there's my U. So I think you used the wrong U. Although I am finding that a little bit more often. I found it a couple of times now. But that's the approach. Although I do like the app. The app's nice. Alrighty, guys.